Welcome to General Structures 2 and Lateral Forces, Lesson 5, Example number 9. And what it says is if a building in Example 2 has a 4-foot high parapet wall with the top at 15 feet above the adjoining ground, how much moment should the wall be designed? For how much moment should the wall be designed? So we need to go back to example number 2, which, hate to say it, I have no idea what it was, so I just need to go back in the study guide. And it is on page 128. And it says, what is the static, horizontal, and vertical wind pressures in pounds per square foot on a flat roof fire station, which is 15 feet high and located in downtown area of Los Angeles using method 1. Okay, so here we go. So I believe we had, that's a fire station, so let's make it look like this. Now, if I believe correctly, we made the fire station have a overhead door type situation, so it looked more like a fire station, so it was very believable. Alright, and then 15 foot here. And then what else? Los Angeles. And I don't really want to go through this again, but I'm going to because I think it helps. It has a flat roof, static, horizontal, and vertical wind pressures in pounds per square foot. Okay, so there it is using method 1. Okay, now we're going to go back to where we were when we were on example number 9. So it says if the building in example 2 has a 4-foot high parapet wall. Oh, it says with the top at 15 above the adjoining ground. Okay, so I'm assuming that 4-foot parapet wall, that's a dashed line. From what I'm reading, it sounds like this is the 4-foot high parapet wall. So the top is still 15 foot. So the first thing we do is we go to the general wind formula is the P equals CE, CQ, QS, I. And if you remember correctly, it's a fire station, so I is the importance factor. I'll go ahead and do that first because it makes the most sense to me. It's the most obvious to me. And I believe since it's more, it's 1.15. And there's a table. I don't remember where that table is located. Let me think. And we'll just trust me on this because I don't remember where the table is. And then we'll go CE, which is the exposure factor. And the exposure factor is, we'll go to table 16H. And on table 16H, oh, scratch that, it's 16G for the exposure factor, which for this it is 0 to 15, and we had said that it is exposure B, I believe. What is number 2? 222. For built up areas, okay, yes, we're saying it's exposure B. So exposure B is 0.62. Meaning it's not very exposed. It's inland, it's not next to a sea, and it's not going to get a lot of wind. It's not in a really flat area. It's in kind of the middle of town. So that's where exposure B is coming from, and that gives that CQ is our pressure coefficient, and this is the one thing that's going to change because it's a parapet wall. If you go to table 16-H, you'll see that it's 1.3 inward or outward for parapet walls. And that's in the first little box there. And you'll see that all structures is 1.2 and roof elements 1.3. Hopefully you remember doing that in the last few exercises. And we also have QS, and that is located on table 16F. And its basic wind speed is 70, I believe. Let's go back to the math. I don't want to tell you. I'm pretty darn sure that LA did not have a special wind speed, and I don't think it is. It's in the 70, which is the basic wind speed, and then we get 12.6 as the QSF, or not QSF, KSF. Is that what it is? PSF. 12.6 PSF. KSF would be a huge wind load. And once again, that's in table 16-F. And there, we have all what we need. So we go CE is 0.62, CQ is 12.6, and that's in PSF. Let's not get that mistaken. No, that was QS. Shoot. It's 1.3. And I, 1.15. And that is just for the parapet right here. And it can be this way or this way. And that's up to you to figure out which way is going to be the worst. So let's go ahead and get the calculator out and calculate what the answer is for that. It's 0.62 times 12.6 times 1.3 times 1.15 equals 11.67. We'll say 11.7. And that's in PSF. Alright, so we have 11.7 PSF. And that's going either way. And to tell you the truth, I forget what this was asking, what we're wanting to find here. Let's go back to page 132, example number 9. It says, if the building blah blah blah, for how much moment should the wall be designed? So it's asking how much moment. And we can look at it as, the way I would look at it is a cantilever, where you have this coming off, and I would just, this is continuous, that's continuating down. I would look at it as you're getting, it's fixed right here. This is the way I would look at it, as a cantilever. It's a simple way to look at it. You could justify looking at it other ways, and tell you the truth, I should see what they do in the actual in the study guide to see if I'm doing it the same way, because I don't want to confuse you. I'm going to go ahead and do it this way, and if I'm wrong, I'm wrong, and then I can tell you why they did it the way they did it. So, and then this would be, it cuts off here. Get rid of that. 11.7 PSF. I forget how big this building was. Let's go back to example number 2, and it says, oh, well, I guess you don't need that. You don't need that at all, because you can divide it by, you can design it by the linear foot, if that makes any sense. And I think it does, so I'm just going to do it, and then you can justify to yourself that that's what they're doing. Alright, and we're going to say that the moment is going to be what this creates. Let's go ahead and change colors. And we're going to say the moment is that. So how do you figure out that? Well, you take 11.7 times 4 foot, right? Because it's 4 foot tall, and then you're going to, and that's going to give you an equivalent load right in the middle, because that's where equivalent load acts on a linear load like this, since it's right in the middle. So this is actually acting at 2 foot. So we have to figure out what this is. 11.7 PSF times 4 equals, I don't like my head math, what should be 44, 46.8. Let's check it on the calculator. 11.7 times 4 is 46.8. And that's kip. This is 4 foot, so pounds per linear foot. So looking, what that does is, here's your parapet, right? And instead of having a load that looks like this, like a box load that's running all the way like that, you now have a load that looks like this, right in the middle. You have this line load, and it's a line load right in the middle of that parapet, 2 foot off the, or 2 foot away from the top. So anyways, let's get rid of that. That's what you're looking at. So this right here is that 46.8 pounds per linear foot. And then to get a moment, you want to multiply that by 2 foot. Right? Force times distance is a moment, 46.8. So let's go ahead and put it down here, 46.8 PLF times your 2 foot. And there you go, what, 93.6. Let's put out my calculator. 93.6. And that is pounds per linear foot times foot. It's just actually pounds, but what I like to do is I like to write this a different way. I like to write this, what am I saying? I like to write this pounds per linear foot. So if you say that's pounds per foot times foot, right? The way I like to look at it is to say foot pounds is your moment per foot. So every linear foot of that wall you're going to have to design for 93.6 foot-pounds. I hope that will make sense, because once you get into concrete design, you'll have to do it like that, or whatever type. This might be a steel frame, so you would have to distribute that over. But that's your answer, that 93.6 foot-pounds per foot. Hope it's not hope it's not too confusing. Let's see what they did in the study guide. 93.6. They must have done the same thing I did. So there's your answer. That's what you have to figure out that moment for. If you have any questions, please just go ahead and type it out, and I'll hopefully respond as soon as I can. I hope that was helpful, and I will see you in the next video.